Hello everybody, welcome to the second video lecture for Erase Physics Mechanics. This lecture is going to be on 2D kinematics as opposed to the 1D kinematics in the first video lecture. And we will see pretty quickly that 2D kinematics is a lot like 1D kinematics. A lot of the skills that you need in 2D kinematics also come from 1D kinematics. So that's why for this lecture, we're just going to be heading straight into an example problem to see what's up. So, 2D with 2D kinematics, you can essentially treat it kind of like two 1D kinematics problems. And the reason for this is because in 2D kinematics, you have two dimensions, obviously, an x-axis and a y-axis or whatever, and you can break vectors and velocities and displacements and things like that into components, like the x component of a vector and the y component of a vector. And using these, you can calculate separately based on these two axes kinematics for, say, an object. So let's get into this problem and give you an example to show you what I'm talking about. So in this example 2.1, an object moves with this acceleration vector 2, 3 and has an initial velocity 1, 2, and you want to find its displacement after 5 seconds. Okay, let me go ahead and draw a graph here. I'll just say that the particle starts at 0, 0 for convenience. It doesn't have to, you can start anywhere, it just asks for displacement. But just for explanatory purposes, I'm going to say it starts at 0, 0. Okay, now let's see. The object moves with an acceleration with x component 2 and has an initial velocity of an x component of 1. So what this means is that it initially starts moving right at a speed of 1, and then this speed increases by 2 per second. By 2 per second. And similarly for the y component, it has initial velocity 3, or sorry, initial velocity 2, and it increases by 3 per second. The velocity increases by 3 per second. So you can imagine what this might look like. You might start with a velocity of 1, 2, and the particle may follow this path, and it'll accelerate both in the x direction. Okay, well, it'll accelerate both in the x direction and in the y direction, like so. Okay, so now that we know this, let's go ahead and find the displacement of our object. Then, when dealing with 2D kinematics, you can often separate the problem into two 1D kinematics problems by looking at the components. So if we look at the x component of this object, well, the displacement in the x direction, this is going to be equal to, we'll just vi, or the initial velocity in the x direction times time, plus 1/2 times the acceleration in the x direction times time squared. And this is just our regular 1D kinematics equation, just applied to the x component. Now, if we go ahead and substitute values in, the initial velocity is 1. We want to find its displacement after 5 seconds. And then we can add 1/2 times the acceleration in the x direction is 2 times 5 squared. And if you calculate this, I believe this turns out to be 30. Yes, it turns out to be 30. Similarly, for y, it's just equal to the y component of the velocity times time, plus 1/2 times the acceleration of the y component times t squared. It's very similar to 1D kinematics. So for y, the initial velocity is 2 times 5 seconds. I don't know why I'm writing my times differently now, but I am. The acceleration is 3, and the time is 5. Okay, actually, I'm going to go ahead and put parentheses just because I feel like it. Okay, and if you calculate this, you should get 47.5. Again, you can just plug this into your calculator. So the displacement of this object is 30, 47.5. And again, I keep on stressing this is a lot like a 1D a 1D kinematics problem, right? Except you can break things up into components, and by breaking things up into components, 2D kinematic equations like this can be easier to solve. All right. All right. Moving on to the next example, example 2.5. Again, like I said in the first lecture, there are, of course, examples before this, and I do recommend that you go through them and make sure and try them out before you look at the solution. And then for the examples before this, look at the solution, and then make sure you understand it. But anyway, for example 2.5, this is dealing with projectile motion. So you can think like when you throw a projectile, right? Uh, it kind of follows this path. Um, and we would and with projectile motion problems, we want to like find out information about this path, right? On Earth, we assume the gravitational acceleration to be constant and downwards, meaning that if there are no other forces on this projectile, the only acceleration on this object the entire time, if there are no other forces besides gravity, it's going to be a constant acceleration of g downwards. G equals 10 meters per second squared. Okay. So now, with this problem, example 2.5, we are given a projectile and we want to find out how far the projectile travels in the horizontal direction before hitting the ground with a initial velocity vi at an angle theta from the horizontal. And we also want to find out what angle theta we could use to maximize the distance the projectile travels on a flat ground. Okay, well, again, we can use our kinematics equations for this. First, it would be nice to find out the time it takes for the projectile to travel in the air, because we know that horizontal velocity is constant because there's only a vertical acceleration, right? And since horizontal velocity is constant, we could calculate the range by doing horizontal velocity times time in the air. Okay. So what is the time in the air? Well, our initial velocity in the y direction is equal to v of I times the sine of theta. Right, this is just vectors. And we want to find the amount of time it is in the air. So one way you could do this is we could note that when the object comes back toward the ground, it has a velocity of negative v of iy. So we could, for example, say, final velocity is negative iy minus, I'll write negative v of I sine theta minus the initial velocity. This is equal to the acceleration of the object times time. And so what this means, acceleration is negative g, by the way, because it points downward. And so if we solve this, we get that time is equal to 2 times v of I sine theta over g. Again, this is just 1D kinematics, just in the vertical direction. Okay, well now that we know the time the object is in the air, we can figure out the distance it travels. Since again, horizontal velocity is constant because there's only a vertical acceleration. There's no horizontal acceleration in projectile problems like these. So the initial x velocity is equal to v of I times cosine theta. Again, just kinematics. Again, just trigonometry. So the distance, the distance the projectile travels is v of I times x times, or v of ix times t, and this is equal to 2v of I squared times the sine of theta times the cosine of theta divided by g. Now there is I'll move this here. There is a trig identity that is pretty useful that you might know from math. This is the sine double angle identity, and it states that for any angle theta, sine of 2 theta is equal to 2 times sine of theta times cosine of theta. And this is just an identity from math that you might want to know. So if we would like, we can combine this 2 and sine theta, cosine theta here to make, v of I x on c, which is the distance. We can say that this is equal to v of I squared times the sine of 2 theta over g. And so this is the horizontal distance a projectile will travel over a flat ground with this initial angle theta and initial speed v of I. Now, if we want to maximize this angle, if we want to maximize this displacement, we can realize that, if we can get sine of 2 theta right here equal to 1, then it'll be like the maximum distance we can travel. And indeed, when when theta equals 45 degrees, sine of 2 theta equals 1, which means that, I'll just say x for displacement, equals v of I squared over g. So when you launch this projectile at an angle of 45 degrees, the projectile will launch at this amount away, and this is the maximum possible range we can throw it with. Okay. So yes, again, here we break the problem down into 2 separate components, and we can use these 2 separate components to solve the problem as a whole. Alright, so now that we discussed about how to solve 2D kinematic problems, I will go over one more trick that you can use for 2D kinematics problems, which is tilting your coordinate system. Okay, so in this problem, Josh stands at the base of this inclined plane that has an angle alpha, and he throws the ball at an angle theta from the plane, and we want to find out what is the time of flight of the projectile. Okay, now this on itself would be pretty hard to solve because, well, you have to keep track of like how far this travels, and if depending on how far it travels, this it could like hit the thing at a different point, and it's pretty messy if you work in this untilted system. But there is a trick. Let me draw this real quick. Okay. Let me draw this like this. There is a little trick you can use. So, in this untilted system, we would have this ball that's flying at some velocity like this and has an acceleration downward. But what if we tilted our coordinate system? What if we tilt our system by just rotating this over by like an angle alpha? Well, then what happens is you get this. Then what happens is you get this flat plane, and you get this flat plane, and you have this ball with an acceleration this way, and a velocity, I don't know, maybe something like this. And this comes just from tilting this entire thing, just tilting it all, just tilting your entire diagram over. Right? It sounds pretty crazy, but you'll see why you do this in a second. Now, we can think of this in terms of the components, right? We can think of this in terms of the components parallel to the plane and perpendicular to the plane. And this is actually a very common trick in inclined plane problems. Instead of viewing this problem as with coordinate system with like your components being x and y, you might analyze it with components parallel and perpendicular to the plane. So in this case, what would be the gravity? Well, the net gravity points like this, right? Again, just tilting this diagram over. That's an arrow in the wrong direction. Tilting this diagram over. But this gravity has its own components. Namely, it has component of g times g times the cosine of alpha, oh, sorry, cosine of alpha downward. All right, you can think of it like this. This is g times the cosine of alpha downward, and g times the sine of theta, or alpha, parallel to the plane. And yeah, so it has these two components of acceleration. And knowing this, the problem becomes a lot easier actually, because now we have this constant vertical and horizontal acceleration, and you can think, right? Oh, you can think out of the ball, and oh, it's gonna fall down like a regular ball, but it's also going to be accelerating this way. So it's gonna like fall down with a slower horizontal velocity, and then maybe it's gonna bounce back or something like this, right? Let me draw this like that. It's gonna bounce back like this, right? And again, it has this. Okay, well, this is not opaque conservation of energy. It's gonna bounce back something like this. And again, there's a horizontal acceleration, but there's also a vertical acceleration, right? Okay, so now knowing this, finding the time of flight of the projectile becomes very, very easy. Now all we have to do is use our kinematics equations in the y direction, because the velocity of the ball in the x direction doesn't affect the time of flight of the projectile. So going ahead and analyzing in the y direction. Well, I think we did this earlier. But you can say, oh, like negative negative v sine theta is the final velocity. By the way, yeah, the velocity this way would be v sine theta, and this way would be v cosine theta. But anyway, the final velocity is negative v sine theta minus the initial velocity is equal to the acceleration, which is g times cosine theta, right? Times the time, or sorry, negative g cosine theta, my bad. And from this, we can really easily just derive that t is equal to 2v sine theta over g cosine theta, or alpha. And you can see how tilting your coordinate system can definitely make calculations a lot easier, because then you can deal with things in simpler components as opposed to maybe more complex equations with things like this. Alright, so that is all for this video lecture. Again, if you have any questions, go ahead and contact if you have any questions, go ahead and contact the instructors. But other than that, do your best on the homework problems, and have a nice day. I will see you later.